Let f and g be functions of a real variable such that g of x is equal to the integral from 0 to x of f of y times y minus x dy for all x. If g is 3 times continuously differentiable, what is the greatest integer n for which f must be n times continuously differentiable? I mean, I think the answer is going to be 2. But, how do I see that? G of x is equal to the integral from 0 to x of f of y, y minus x dy. If I just start taking derivatives of this, when I take let's write this, let's change this up a bit. G of x is equal to the integral from 0 to x f of y, y dy, minus x integral from 0 to x of f of y dy. If I take a derivative of this, then I don't actually have to take a derivative of f just yet. When I take a second derivative, I will have to take a first derivative of f. But I wonder if maybe at some point there's a cancellation of some sort where we don't need the second derivative or something, so maybe we can conclude, or like maybe the answer is 1 because of something. I'm just going to take the derivatives. My instinct is that the answer is 2. Yeah, so this is why I believe the answer, this is why you have to be careful. There's a cancellation here. Why is this not erasing? I can't erase things for some reason. Okay, ignore that. So g prime of x is equal to negative integral from 0 to x f of y dy. So g double prime of x is equal to negative f of x dx, just f of x, and g triple prime of x is equal to negative f prime of x. So the answer is in fact 1 because of this cancellation. Let me just make sure that I did these computations correctly. G prime is f of x times x by fundamental theorem of calculus. Here I've used product rule. Derivative of x is 1, left with the integral, minus x times the derivative of this, which is f of x. Those cancel. These things here cancel. And so I have g prime is the integral, the negative integral of f. Yeah, so we only need one derivative of f to exist. What is the greatest integer n for which f must be? So it must be once differentiable. It doesn't have to be twice differentiable. This still works. Yeah, so that'll be my answer. Yeah, my instinct was 2, of course, simply because normally with fundamental theorem of calculus, if a function is inside an integral like this, then you need to differentiate it one more time to get its derivative out. But I guess this is one of the, I don't know if there's like a really nice, convenient, easy way of identifying that the answer is not 2 here without just going through the computations. But nice little problem. Thanks for watching.